NENOMATICA, where mathematics meets YouTube excellence. Welcome to our video on the 14th property of inequalities. Today, we'll explore how inequalities behave when we take the mth root of both sides. Let's begin by understanding what this property tells us. The property relates to taking the mth root of both sides of an inequality, but the behavior depends on whether m is even or odd. Let's start with the first case. When we have a is less than b, and m is odd, specifically m equals 2k plus 1, where k is a non-negative integer, we can take the mth root of both sides and maintain the same inequality direction. For example, when m equals 3, which is 2 times 1 plus 1, or m equals 5, which is 2 times 2 plus 1, we preserve the inequality direction. Now, let's look at the second case. When 0 is less than which is less than b, and m is even, specifically m equals 2k where k is a positive integer, we can again take the mth root and maintain the same inequality direction. For example, when m equals 2, which is 2 times 1, or m equals 4, which is 2 times 2, the inequality direction is preserved. But notice the important condition here. Both a and b must be positive. Let's consider the third case. If a to the power of m is less than b to the power of m, and m is odd, specifically m equals 2k plus 1, then we can deduce that a is less than b. This is essentially the reverse of our first case. For example, if a cubed is less than b cubed, we can say a is less than b because 3 equals 2 times 1 plus 1. Finally, let's examine the fourth case. If a to the power of m is less than b to the power of m, and m is even, specifically m equals 2k, then we can deduce that the absolute value of a is less than the absolute value of b. For example, if a squared is less than b squared, we can only conclude that the absolute value of a is less than the absolute value of b. This is because squaring eliminates the sign information. Let's visualize case 1 with an example. Welcome to our math lesson today. We'll be exploring the 15th property of inequalities, which deals with powers and roots of numbers based on their magnitude. Before we dive into this property, let's establish our prerequisites. We'll be working with natural numbers m and n, where m is less than n. Let's start with the first case, when a is greater than 1. First, if a is greater than 1 and m is less than n, then a raised to the power of m is less than a raised to the power of n. Second, if a is greater than 1 and m is less than n, then the nth root of a is greater than the mth root of a. Now, let's examine the second case, when a is between 0 and 1. First, if a is between 0 and 1, and m is less than n, then a raised to the power of m is greater than a raised to the power of n. Second, if a is between 0 and 1, and m is less than n, then the nth root of a is less than the mth root of a. Let's visualize these properties with some examples. Example, consider a equals 2, m equals 2, and n equals 3. Since a is greater than 1, we know a raised to m is less than a raised to n. Let's calculate. 2 squared equals 4, and 2 cubed equals 8. Indeed, 4 is less than 8, confirming our first property. For the second property, the nth root of a is greater than the mth root of a. The cube root of 2 is approximately 1.26, while the square root of 2 is approximately 1.41. Since 1.26 is less than 1.41, this confirms our property. Now, let's examine a case where a is between 0 and 1. Example, consider a equals 1/2, m equals 2, and n equals 3. Since a is between 0 and 1, a raised to m is greater than a raised to n. Let's calculate. 1/2 squared equals 1/4 or 0.25, and 1/2 cubed equals 1/8 or 0.125. Indeed, 0.25 is greater than 0.125, confirming our third property. For the fourth property, the nth root of a is less than the mth root of a. The cube root of 1/2 is approximately 0.794, while the square root of 1/2 is approximately 0.707. Since 0.794 is greater than 0.707, this confirms our property. Let's understand why these properties hold true through graphical representation. For powers, where we'll be proving two important inequalities. The first one is the well-known triangle inequality, which states that the square root of a squared plus b squared is less than or equal to the absolute value of a plus the absolute value of b. Let's start with our first inequality. We need to prove that the square root of a squared plus b squared is less than or equal to the absolute value of a plus the absolute value of b. To prove this inequality, we'll start by using the property that if two non-negative numbers are being compared, we can square both sides without changing the inequality. Now, let's simplify the left-hand side. The square of the square root is just the expression inside the square root, so the left side becomes a squared plus b squared. Next, we'll expand the right-hand side using the square of a binomial formula. The square of the sum of two terms equals the sum of their squares plus twice their product. Since the absolute value squared is just the value squared, we can simplify further. The absolute value of a squared equals a squared, and the absolute value of b squared equals b squared. Let's rearrange to isolate the terms that are different on both sides. Now, since the product of two absolute values is always non-negative, the expression 2 times absolute a times absolute b is always greater than or equal to 0. This means our inequality is always true, which proves the original inequality. Now, let's move on to our second inequality. We need to prove that a over b is less than a plus k over b plus k, given that a, b, and k are all positive numbers, and a is less than b. Let's start by listing what we know. We have it as less than b, and k is positive. Since k is positive, and a is less than b, we can multiply these inequalities. Multiplying a is less than b by k, we get a times k is less than b times k. Now, let's add a times b to both sides of the inequality. We can factor out a from the left side and b from the right side. Now, we'll divide both sides by the product of b times open parenthesis k plus b close parenthesis. Since a, b, and k are all positive, this product is also positive, so the inequality sign doesn't change. Let's simplify both sides. On the left, we can cancel out k plus b, leaving a over b. On the right, we can cancel out b, leaving k plus a over k plus b. And there we have it. We've proven that a over b is less than a plus k over b plus k, given our initial conditions. We need to prove the following inequality. The fraction a cubed plus b cubed over 2 is greater than or equal to the quantity a plus b over 2 cubed, where a and b are both positive numbers. Let's solve this step by step, following a careful algebraic approach. Let's begin our proof. Since a and b are both positive numbers, we can use a fundamental property that the square of any real number is always greater than or equal to 0. So we can write a minus b squared is greater than or equal to 0. This is true for any real values of a and b. Next, we'll expand the square using the algebraic identity for the square of a difference. So, a minus b squared equals a squared minus 2ab plus b squared, which is greater than or equal to 0. Now, we'll rearrange this inequality to a more useful form. We can rewrite it as a squared plus b squared is greater than or equal to a times b plus a times b, which simplifies to a squared plus b squared is greater than or equal to 2ab. Let's simplify this further. We get a squared minus ab plus b squared is greater than or equal to ab. And remember that we have the constraint that a plus b is greater than 0, which is satisfied because we assumed a and b are positive. Now, since a plus b is positive, we can multiply both sides of the inequality by a plus b without changing the direction of the inequality. When we multiply both sides, we get a plus b times the quantity a squared minus ab plus b squared is greater than or equal to a plus b times ab. Now, we need to expand the left side of our inequality. This gives us a cubed plus b cubed is greater than or equal to ab times a plus b. Now, if we multiply both sides by 3, we keep the inequality in the same direction. This gives us 3 times a cubed plus b cubed is greater than or equal to 3 times ab times a plus b. Let's expand the right side of our equation. 3ab times a plus b equals 3a squared b plus 3ab squared. Now, let's add a cubed plus b cubed to both sides of the inequality. This gives us 3a cubed plus 3b cubed plus a cubed plus b cubed is greater than or equal to 3a squared b plus 3ab squared plus a cubed plus b cubed. Let's simplify the left side by combining like terms. We get 4a cubed plus 4b cubed is greater than or equal to 3a squared b plus 3ab squared plus a cubed plus b cubed. Now, let's observe that the expression on the right side matches a pattern we know, the cube of a sum. Specifically, the right side is equivalent to a plus b cubed. So our inequality becomes 4a cubed plus 4b cubed is greater than or equal to a plus b cubed. Now, let's divide both sides of our inequality by 8 to move closer to our goal. This gives us 4a cubed plus 4b cubed divided by 8 is greater than or equal to a plus b cubed divided by 8. Let's simplify this division. 4a cubed plus 4b cubed divided by 8 equals 4 times a cubed plus b cubed divided by 8, which equals a cubed plus b cubed divided by 2. For our final step, let's simplify the right side of the equation. A plus b cubed divided by 8 equals the quantity a plus b divided by 2, all cubed. And with that, we've proved the inequality that a cubed plus b cubed over 2 is greater than or equal to the quantity a plus b over 2 cubed for any positive values of a and b. Welcome to this math video where we're going to solve and verify an inequality. Let's look at the following problem. We need to prove that the inequality a plus b divided by 1 plus a times b is less than 1, given that both a and b are between 0 and 1. Let's first note that since a and b are both positive, their product, ab, is also positive. This means 1 plus ab is greater than 0, so our denominator is always positive. Now, let's start solving the inequality. First, we'll restate our main inequality. Step 1. We need to multiply both sides by 1 plus ab. Since we've established that 1 plus ab is positive, multiplying both sides by it won't change the direction of the inequality. Step 2. Now we can simplify. On the left side, the denominator 1 plus ab cancels with the term we're multiplying by. On the right side, we get 1 plus ab. Step 3. Let's rearrange to get all terms on the left side. We'll subtract 1 plus ab from both sides. Step 4. Simplify the left side by distributing the negative sign. Step 5. Let's rearrange the terms to group similar ones. We can rewrite this as a minus ab minus parenthesis 1 minus b is less than 0. Step 6. We can factor out common terms. For the first group, we can factor out a, and for the second group, we can factor out 1 minus b. Step 7. Now we can factor out the common term 1 minus b from the entire expression. Step 8. Now, let's check the signs of each factor. Since b is between 0 and 1, 1 minus b is positive. And since it is also between 0 and 1, a minus 1 is negative. So when we multiply a positive number, 1 minus b, by a negative number, a minus 1, we get a negative result. This means our inequality 1 minus b times a minus 1 is less than 0 is satisfied. Therefore, the inequality 1 minus b times a minus 1 is less than 0 is always true when 0 is less than 1 and 0 is less than b is less than 1. This means our original inequality, a plus b divided by 1 plus ab is less than 1 is proven to be true. Welcome to our math lesson today. We're going to prove an inequality using algebraic techniques. Let's start by looking at the inequality we need to prove. Our example today is to prove the following inequality. The square root of a plus the square root of b is greater than the square root of a plus b, where a and b are both positive numbers. Let's follow a step-by-step approach to prove this inequality. The first step is to restate what we're trying to prove. The next step in our proof is to square both sides of the inequality. This is allowed because both sides of our inequality are positive, so squaring preserves the direction of the inequality. Now, we expand the square on the left side. We use the formula a plus b whole squared equals a squared plus 2ab plus b squared. Next, we'll simplify our inequality by subtracting a plus b from both sides. We can simplify the expression further by using the property of square roots. The square root of a times the square root of b equals the square root of ab. Now, we need to check if this inequality is true. Since a and b are both positive, their square root product is also positive. So 2 times the square root of a, b is definitely greater than 0. Therefore, our original inequality is always true for positive values of a and b. Let's start by looking at our problem. We need to prove the inequality. Square root of a plus square root of a plus 2 is less than 2 times square root of a plus 1. Let's follow the solution process exactly as shown in our algorithm. First, we'll rewrite the right side of our inequality. We can express 2 times the square root of a plus 1 as the square root of a plus 1 plus another square root of a plus 1. Next, we'll rearrange the terms in our inequality. We'll move the square root of a plus 1 from the right side to the left side by subtracting it from both sides. This gives us square root of a plus 2 minus square root of a plus 1 is less than square root of a plus 1 minus square root of a. For step 3, we'll multiply both sides of the inequality by fractions. On the left side, we'll multiply by the fraction square root of a plus 2 plus square root of a plus 1 divided by the same expression. On the right side, we'll multiply by the fraction square root of a plus 1 plus square root of a divided by the same expression. This will help us rationalize the expressions and simplify our work. For step 4, we'll apply the difference of squares formula. We know that the product of the difference and sum of the same terms equals the difference of their squares. So on the left side, we get a plus 2 minus a plus 1 over square root of a plus 2 plus square root of a plus 1. Similarly, on the right side, we get a plus 1 minus a over square root of a plus 1 plus square root of a. In step 5, we'll simplify the numerators. A plus 2 minus a plus 1 simplifies to 1, and a plus 1 minus also simplifies to 1. So we get 1 over square root of a plus 2 plus square root of a plus 1 is less than 1 over square root of a plus 1 plus square root of a. In step 6, we'll take the reciprocal of both sides. Since we're taking reciprocals, the direction of the inequality flips. So we now have square root of a plus 2 plus square root of a plus 1 is greater than square root of a plus 1 plus square root of a. For the 7th step, we'll simplify the inequality by canceling the common term square root of a plus 1 from both sides. This gives us square root of a plus 2 is greater than square root of a. For our final step, we need to determine if the last inequality, square root of a plus 2 greater than square root of a, is always true. Since a plus 2 is always greater than a for any value of a, the square root of a plus 2 is always greater than the square root of a. This means the inequality is always true, and therefore our original inequality square root of a plus square root of a plus 2 less than 2 times square root of a plus 1 is always valid. Let's summarize what we've learned. In this problem, we proved the inequality square root of a plus square root of a plus 2 is less than 2 times square root of a plus 1. We used several key techniques. First, rewriting the right side of the inequality. Then, rearranging terms and using the rationalization technique. We applied the difference of squares formula to simplify expressions. Finally, we worked with reciprocals and verified the resulting inequality. This type of problem is important in mathematical analysis and demonstrates how to work with inequalities involving square roots. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.